It's a PowerPoint. It's a Microsoft product. That's what's causing it. What's that? I know they over the weekend. Mine disappeared last night. Dr. Swanberg disappeared. There's a trash can hog somewhere that's eating all the trash cans. Yeah.
They're trying to create an intramural office basketball team.
Right. Okay. And then why does it reduce the size? I don't know. It's a Microsoft product. I don't like Microsoft, by the way, if you hadn't noticed. Okay, I have two arrows on the page. Which one were we at?
I don't know. Just now got it.
Explicit and implicit solutions? Or
implicit solution of ODE.
we did that, the definition, implicit solution of ODE, the relation g of x, y, 0 equals 0. Yeah, we did that.
Yeah.
That was probably the last thing, right?
Yeah, what page is that?
That's at the bottom of page 6, moving to the top of page 7.
Yeah, that's it.
All right, then, it says here it is beyond the scope of this course. Sure, yeah. I'm so used to looking to make sure my volume is good and that kind of stuff. I can't see that anymore. Okay, it is beyond the scope of this course to investigate the conditions under which the relation g of x, y is equal to 0 defines a differentiable function phi. So we shall assume that if the formal implementation of the method of solution, yeah, blah, blah, blah. Let's just do example 5, okay? Yeah. All right. Here's in a relation, okay? All right. The relation x squared plus y squared is equal to 25. Okay? Now, this is a big pain in the neck here. I'm trying what you suggested, letting this bump against the pile of books. But last time it knocked things over, but hopefully I won't press this hard. All right. That's an implicit solution of a differential equation. They're just telling you that dy dx is equal to minus x over y. Okay? On the open interval, minus 5 to 5. Okay? Now, I think this is all they're getting at. How do you verify that that statement's true? Okay? There would be one possibility, I'm not saying I would do this, you could try solving that for y, okay? But you wouldn't have a function, right? Because when you do y squared is equal to 25 minus x squared, and then take a square root of both sides and you get plus or minus, then you have to do one function and the other function. It would be two different functions. And that would be somewhat of a pain in the neck. Much simpler to do is what we call implicit differentiation. You remember how that ran? Okay. You're differentiating with respect to x. So it's d by dx of that plus d by dx of this plus d by d is equal to d by dx of that. Basically is what you're doing. Those are dx's there, okay? So what is d by dx of x squared? 2x. Plus, now how do you do d by dx of y squared? Sorta. Okay. It's chain rule. Okay. a 2y, and then you do a dy dx. Okay, right? And that's equal to, and what is the derivative of 25? 0. Got it. Now we solve this for dy dx, right? So we'll subtract 2x from both sides, and that gives us 2y, because this goes to 0. 2y dy dx is equal to minus 2x, right? Then divide by 2y. Yes, you get minus x over y. So sure enough, that's true. Now, why do they say on the infinite interval minus 5 to 5? Okay. Well, let's go back to that first thing I said you could try, but I wouldn't recommend it. But if you had done that, you would have y squared is equal to 25 minus x squared, and when you try to take a square root of that, you have to stay inside that, because otherwise in complex land. Z-plane. Okay. Yeah. All right. So you're out there. So that's why you stay between minus 5 and 5. Now, why isn't it close interval minus 5 to 5? I'm not really sure. Okay. Oh, yes, it is. Huh? You can't what? I really can't see why not, except that if you went to 5, then that sure enough would be a 0, and with y equals 0, you can't do that. So that's why it's open. Because for that, you could go to 5, but for this, you cannot. So that's why. Okay. So, by implicit differentiation, we obtained that, and sure enough, I just did what they did. I didn't realize they were doing it. Okay. Now, and the other part I said, you could have done, and they were actually doing it both ways. I should have read ahead. You could have, exactly like I said, these are plus or minus, and the first function they're calling a phi1, and I can't help but feel like they're saying phi because that's the closest thing they got to elf in the Greek system. You know, phi and elf, you know, they sort of sound almost alike. Phi1 of x would be, say, the positive square root of 25 minus x squared, and phi2 of x would be minus the square root of 25 minus x squared. Those would be the two functions, and then you take your derivative of each one of those. And so yeah, by the way, and you got your book, so I'm not going to draw it, but you see this, oh, here it is. This equation we started with, x squared plus y squared is equal to 25, that was, that's the circle of radius 5. Right? So the one function is the one at the top half and one at the bottom. Right, exactly. So this will work, as they say here, for any relation of the form x squared plus y squared minus c, where c is a positive number, formally satisfies this thing right here. Leave off the plus or minus 5 here because that was specific for what the value of c was. But all right, Victor's here. What's that? I can't hear. Yeah, it is, and we'll get there in a minute. No, you don't have a book yet, or do you? Okay. I'll start writing more on the board then. And by the way, this is when I went to record the last class, when I hit that first record, it said you only have memory for 50 minutes. So I think at the end of the last class, it just rounded to the nearest half hour. And that's why it said you've reached the max, an hour and a half. It just sort of threw that in. This morning it said you got 50 minutes left. I got rid of all those files, and now I didn't get that message. So I think we're good. Hope we're good for a while anyway. Okay, we're had some memory issues besides my forgetfulness. The computer had memory issues. Okay. Now, they said any equation, I'm picking up, any relation of the form x squared plus y squared minus c is equal to 0. See, they took basically what we had there and what's that? Yeah, exactly. And they're trying to make it generic now, but that only works when c is positive. It says it formally satisfies this equation right here without this part in it, okay? What's that? I can't hear. Okay, negative 25? Try it, you won't like, I know. It's, that's what they were just saying. Any relation of that form formally satisfies that for any constant c. However, it is understood that the relation should always make sense in the real number system. For example, if c is equal to negative 25, then you can't say that x squared plus y squared plus 25, because if it's a minus 25 minus the minus is that, equals 0. Try that and see if you can ever get that to work. You can. Because if x is negative 0, y is 0, you got 25. Any other value, you got something greater than 25, okay? So you're never going to equal 0. So then you would have to be in the complex system, Z-plane, and we're not doing this there. Not in this course anyway, okay? Because this distinction between the explicit solution and implicit solution should be intuitively clear, we will not belabor the issue by always saying, here's the explicit or implicit solution. So we just have a lot of verbiage here. Now, what you are referring to the bottom of this page is a family of graphs, families of solutions. The study of differential equations is similar to that of integral calculus, but different, okay? Similar, okay? In some texts, a solution phi is sometimes referred to as integral of the equation, and its graph is called the integral curve. When evaluating an antiderivative or indefinite integral in calculus, we use a single constant c of integration. Analogously, when solving first-order differential equations, let's go to a clean, okay. This is the one, that I remember. When I'm in PowerPoint in another class, actually using PowerPoint, and this is what was confusing me so badly, I can't go and erase the whole thing. If I'm using a white screen, I can't erase the whole thing, and I have to unwhite it. This one I can because it's a different animal, but it's not intuitively obvious, but it should be, I guess. Okay. Anyway, I'm still learning this this beautiful screencast-o-matic. Okay. So when solving a first order differential equation, and this is one way to express it, f of x, y, y prime equals 0. Okay? That's a first order differential equation. And we're saying nothing about its linearity, and we're assuming, of course, that it's ordinary, not a partial differential equation. So when we're doing that, we usually obtain a solution containing a single arbitrary constant or parameter c. So first order, we'll usually get a parameter c. Okay? A solution containing an arbitrary constant represents a set G, okay, of x, y, and c, okay, equals 0, okay, of solutions called a one-parameter family of solutions. When solving an nth order differential equation, where you got n derivatives, that would be comma y double prime, comma y triple prime, comma dot 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 up to y the nth order differential equation. Then you would have typically have an n parameter family of solutions. Okay? And that n family of solutions, its solutions then would be G of x, y, C1, C2, C3, dot, 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 up to C sub n. So for every order derivative you have, then you introduce another constant in your solution. Okay. I think their verbiage here gets in the way of understanding it. I do not like the way this guy writes. It's the best book I've found so far, but I don't like the way he writes. Okay. This means a single differential equation can possess an infinite number of solutions corresponding to an unlimited number of choices for the parameters. The solution of a differential equation that is free of arbitrary parameters is called a particular solution. This section is focusing on verbiage, on definitions, on things. We're going to come back and run into these things again. This section is just introducing the nomenclature to you. Okay. So here's example 6, which I think is exactly what Cameron doesn't like. Okay. The one parameter family, y, is equal to cx minus x cosine x, is an explicit solution to the linear first order equation x y prime minus y equal x squared sine x. Okay. And it's true on minus infinity to infinity, the whole real number line. Okay? Now it says verify that. How will you verify it? No, start with the y and work forward. Okay.
Just take the derivative.
Okay, yeah, take a derivative. Y prime is equal to C, yes, that means yes in Spanish, okay.
That would be positive
Plus
x sine x
x sine x minus
minus sine x.
cosine x. Right?
Yeah, you got to do the product.
Right, product rule. Okay. So let's see if that works down here. So this would be x times that. That would be cx plus x squared sine x minus x cosine x minus y is cx plus, you could put the y in parentheses or just remember your signs, plus x. All right. You look familiar. I know I've seen you somewhere before. Okay. Javon, is that how you pronounce your name?
Yeah.
Okay, Javon is here. Okay. Good to see you again. All right. Okay. You have a book yet? Not yet? Okay. Well, I was going to tell you what page you were on. Page 7 for your non-book. Okay. We're plugging in. Okay. We were told that this first line here was the solution for the third line, that differential equation. So we're trying to verify that by figuring out what y prime is on the first line and then plugging that into the third line. Okay? That's what we're in the process of doing, and we were just at the point of doing minus y, and y was this, that's minus cx minus a minus, which is plus x cosine x, okay, and supposedly that's equal to x squared sine x. That's what we're trying to show. Well, sure enough, here you have a cx minus cx, those add to 0. You have a minus x cosine x plus x cosine x, those add to 0. And sure enough, we have x squared sine x is equal to x squared sine x. That does equal. So sure enough, that is a solution for this. Now it's a one parameter solution, c being the parameter, okay? And that makes sense because this is a first order linear differential equation, okay? Just happens to be linear. Okay, so sure enough, we do have a single parameter system there. Now, what does that look like? And that's what the picture at the bottom does. So you look at several different c's. When c is equal to 0, then c is equal to 0, it would be y is equal to minus x cosine x. Okay? When x is equal to 0, certainly that would be 0. And when x was anything slightly positive, then this would be going negative from 0 because x is positive, cosine x is positive, and it goes from there. If x was negative, then that would be a positive value because as long as it's small enough, less than pi halves, then this would be positive, and that would be x negative, but less than pi halves. This is still positive because cosine is positive on either side of this. So that's positive, that's negative, but plus minus and minus is positive. So that would be going up. So these things down here should be going up to the left and down to the right. And sure enough, they are. The blue line is when c is equal to 0. Okay? This is referring to your book, and two of you don't have it. It's not an easy thing to reproduce. I'll try to do it best I can. By the way, I did see Rena the other day, and she said she was going to try to be here today, but she had to work it out with her work. Okay, at 0, we're 0. And let me, since they did this in blue in the book, let me do a blue here. I think they had a nice, pretty light blue here. So you had 0, 0, and then when x was positive, you went down a little ways. When x was negative, you went up. Okay, that's all I'm going to do for now. Okay, let's move on out a little further away, where say x is equal to pi halves. That'll be a good first point. X equal pi halves, and we've got c is equal to 0. Remember, that's what the blue stands for, c is equal to 0. Yuck, I keep picking up my pen. Okay, c equals 0. Okay, so when x is equal to pi halves, this of course is 0. Sine of pi halves is 1, so this will be pi halves. Cosine of pi halves is 0. Okay, so you've made your way up to pi halves. Or actually, oh, I was looking at the wrong one. Sorry. This one. Okay. This is 0, and this would be 0. So at pi halves, you're back to zeros. So it went here and came back to 0, and here and came back to 0. If you do on the minus pi halves, you can just go the other way. All right. Now let's go up to pi. Yeah, to pi. Okay. And of course, that first one is 0, and this would be x equal pi, so that would be minus pi. Second, positive pi, because I was just going to say cosine of pi is minus 1, so that would be a positive pi. So you'd be up here at pi. I'm just going to estimate it here, and down here you would be at negative pi. Okay, keep on trucking, and when you get to 3 halves pi, you come back to 0 here and 0 here, and 2 pi, you'll be down here and up here. So you see you got this oscillating curve that's getting, bigger and bigger that way and bigger, ugly curves. Okay, that C is equal to 0. Now let's do C greater than 0. Why not 1? Okay, so let's pick a nice color for that. What color you want? C greater than 0. Red? Huh? Green. No, that's C less than 0 in the book. Okay, so let's put red for C greater than 0. If I can find my cursor. There, I'll do it this way. There. All right. So, when C is greater than 0, we're going to call it 1. What do we have now? Go up here to this one. When x is 0, the first term 0, second term 0. So you're again at 0, 0. When x is equal to, so we're going to have C equal 1. Okay? Let's go again to pi halves. And this will be pi halves minus 0. So this will be, whereas this was down here before, this will be, I think it's like that. Yeah. And everything will just be accentuated. The zeros will still be zeros, and the, no, I didn't quite do it right. Let me erase that. This is a pain.
You have to erase it all.
No. Just all of this. Okay.
Do it all.
Huh? Yeah, anywhere for a last bit. Okay. I think I have to erase this too. I think I got that wrong too. Okay. Well, it really gets to be somewhat of a pain, but let me just suggest to you what's happening now. Yeah, I got to get rid of the eraser pen. Okay. Now, this doesn't come as low, and it's elevated here and elevated here, but probably not doing this quite right, but it's above here. In other words, but down here, it actually, it's below it here. So basically, what you get, your linear term in C starts elevating this way. When C is negative, it drags it that way. So with a negative C, and what color they do? That was the green. So let's do the green. Oops, color green. You've been wanting green. Okay. This will be C equal -1. And probably I should have done something greater than 1. What happens here, this dips lower than this and doesn't come as high and stays below that, but here it goes above it and stays above it like this. So basically, since it's linear in C, as the C's go negative, you have a slope negative here. Think of that. C goes positive, it slopes upward like that, but your basic function keeps kind of its same shape in there. Obviously, by my drawing, that's hard to see. But if you had your book and look at it, that's indeed sort of what's happening. Can you kind of visualize that? Looking at the book? Yeah. So that's what's happening. That's your one parameter family, y is equal to cx plus. Linear in C, but then has the variation for the cosine x. Yeah.
Any first order linear differential equation, your graph will look like that.
Okay.
But greater than 0, less than 0, 0.
I hesitate to say everyone will do everything anytime. You almost have to just play around with it yourself. What I'm saying, this is a linear differential equation, but I'm saying this thing is linear in x. This is a linear term, that's a cosine term. This is a cosine with an envelope that's like this, and that's why that first one is small here, bigger, and it is exploding as you go up. So I'll use black maybe to to show the envelope. Why not? Okay. That first one, the blue curve. There's an envelope like this and an envelope like this. Or should be. And your cosine is going in between there, but it can't be a pure cosine because it's x cosine x, so that sort of messes things up there. Then your cosine curve stays in that. That's the blue curve, C is equal to 0. Then when you have a linear term in front of it, that then takes this graph and gives it a slope. Up here if it's positive, down there if it's negative. That's what I was trying to draw poorly, okay? And I succeeded in drawing it poorly, okay? So that's sort of what you have. Now this one, I really hate to say, and it'll always be like this because it really won't necessarily. All right, now the solution of that blue curve, the C is equal to 0, that basically throws this away, and then you have y is equal to minus x cosine x, okay? I don't know what they're heading at here. Let's see what we're supposed to do with that problem. Okay, the B part of that says the two parameters, okay, this is a separate problem, okay? So let's clear this. Can I clear this? I have to remember which ones I can use in which mode. The two parameter family, y, this is a new function, y is equal to c1 e to the x plus c2 x e to the x. Okay. That's an explicit solution of this. Now, what order differential equation would you guess this to be? Nope. Two parameters, second order. Remember, Yeah, if you go back to, I know some of you don't have books, but go back to the middle of that previous page, isn't that it? Yeah, one parameter would have one C, and an n parameter family would be for an nth order pot. Okay, so this is a solution for a second order differential equation. This happens to be it. Y double prime minus 2y prime plus y is equal to 0. Okay? Now, it claims that. Do you believe them? You probably do, but don't be gullible. Let's verify. Okay? What would you have to do? Take a derivative. Y prime would be what? Isn't this fun? E to the x, right? Plus,
Would that be considered a product rule?
that is a product rule, yeah.
So then it would be E to the X.
C2 e to the x, right? Oh, you were still on the first one?
Yeah.
Oh, I'm sorry.
And then
Okay, well, I can erase that if I've gotten in your way. Just takes a while to get to it, but I can erase it. Okay. All right, you did the first one. Whoops. This is such a fun program. Okay. All right, so sure enough, the derivative of this is C1 e to the x.
and that's it.
Now, the second term, what's this derivative?
That would be C2X.
C2x, C2x e to the x. That's the first product, plus C2 e to the x. Got it. Y'all remember the product rule, right? You know how we got that. Don't hesitate to ask. You see how we got it? Yeah or nay? You do? Okay? All right. Now we also need the second derivative, so y double prime would then be what? There's a part of me that wants to simplify that a little bit, but let's just do it. What is y double prime? C1 e to the x, okay? C2 what? X e to the x, I'll buy that, plus C2 e to the x. That takes care of the second term, plus C2 e to the x. All right, we got stuck in a groove here, didn't we? We can simplify that a little bit. That would be C1 plus 2C2 yeah, I really want to simplify it all. Okay, let's stop this for now. I'll come back and do it in a second. Yeah, let's do our y prime. I'm going to simplify that. Y prime is equal to, every term has an e to the x. Let's pull that out. And then what do we have left? C1 plus C2 plus C2x. Right? Okay, so let's do the same thing to y double prime. Every term has an e to the x, so let's pull that out. And then what do we have left? C1 plus 2C2 plus C2x. Okay, that's a little easier to deal with, isn't it? Maybe? I don't know. So let's plug that in.
Left your 2.
What's that?
You left off your 2C2.
Left off what?
The middle term should be 2C2, right?
Oh, I left off the.
In the okay, sorry, I was looking at y prime and it's double prime. Sorry. You
Yeah.
got it right. You're good.
Okay.
I was looking at the wrong one.
Okay. I don't need parentheses and brackets too, but whatever. Okay. The y double prime is e to the x times c1 plus 2c2 plus c2x minus 2 e to the x times c1 plus c2 plus c2x. Right? Plus, and y is, let's rewrite that too, e to the x times c1 plus c2x. Right? So that'll be e to the x times, why do I put parentheses and brackets? I don't know. C1 plus C2x. Okay. Supposedly, that's equal to 0. That's what our differential equation tells us. Let's see what we've got. Now, will you buy this statement? E to the x can never be 0. Right? Everybody believe that. E to the x never is 0. Always positive. Approaches 0, but never gets there. So basically, I could divide that out. Okay? It's never going to be 0, so it can't factor to be 0. So, well, let's just pull it out. E to the x. Okay. Everything. Now, what do we have left here? C1 plus 2C2 plus C2x minus 2C1 plus, no, minus, yuck, I hate that, I hate this, I hate it, I hate it. I have to go through all this to do that. Pen. Okay. Minus 2C2 minus 2C2x, right? Plus C1 plus C2x equals 0. All right. Pulled e to the x out of everything. And this is what I was left with. Everybody buy that. Okay, now let's see what we've got here. C1 plus C1 is 2C1 minus 2C1 is 0. Okay, here we have a 2C2 minus 2C2, that's equal to 0. Here we have a C2x plus C2x, that's 2C2x minus 2C2x, that's equal to 0. So sure enough, our thing, the right-hand factor is 0 times e to the x, which is never 0, by the way. That's going to be equal to 0. So sure enough, that works. Okay? Now, all we did was verify that's true. That's an explicit solution for that differential equation. Okay? It says verify. We just did. It was also referring back to example 3b, by the way, whether that's important or not. Okay, it says then they drew a picture of this. Oh, my word. And I sure don't want to go there. And y'all don't have a book. I wish I had PowerPoints for this. All right.
Imagine spaghetti.
Yeah, sort of. what we're interested in is this thing right here. We're just going to try to graph that. So I'm trying to think of the easiest way to do it. Probably to erase everything and rewrite that. So let's erase all ink from the slide. And I'll regret that almost immediately. And here was our function. Y is equal to C1 e to the x plus C2 x e to the x. Right. Okay. Now, how does that graph? Okay. Now, when x there's just so many different things that it's really hard to do. Okay. When x is negative, e to the x is going to 0, right? You're going to 0, okay? And that e to the x is going to 0, okay? So down here, everything's going to 0. Now, if C1 and C2 are huge, it may take a long time getting there, but they're ultimately going to 0, okay? Even though x is a negative number and it's trying to make it bigger, e to the x wins. It goes to 0 faster. So ultimately, all these wind up down here. So this is a lousy way to do it, but let's just pick, they have what? 1, 2, 3, 4, 5, about 6. So let's choose, we'll keep one black. Yeah, they have 3. But I'm going to do 1. But they don't even identify what the things are. So one of their blacks does something like this. Whoa. There we go. Something like that, right? Not. It comes out much sharper than that, okay? Now let's do another one. And let's do a red, okay? The red does something like that, okay? Let's do a sort of a tannish, and let's see what we want this to do. Let's do another black. It does something like this, okay? I probably should have saved that for, okay? Let's do another one. I know this is, I don't see how this is really very instructive, but I'm trying to reproduce what they have in the book. Let's do a green one. And their green one does something like this. Okay? It goes up faster. Let's do another one. Blue. They have a blue that does something like this. Okay, only, well, there's a whole bunch of them. Let's see, is there one more maybe? Purple. Why not? Maybe the purple does something like that. Okay. Now, what does that tell you? I don't know what it's trying to say. Except when x gets very, very small negative, it's going to 0. All these are doing this here. So what's happening over here? Well, it depends. If C1 and C2 are both positive, then you're obviously going to go up. That would be something like the green curve here. They're never negative. E to the x is never negative. Oh, wait, I'm sorry. It could be negative down here, perhaps. But if C1 is greater than C2, then you would always be positive here. Now, if in certain conditions, you could wind up going up, others going up and then coming back down, and that would be probably dependent on, this would be a negative here, this is going to win over that. For larger x's, it's going to be greater than this, so finally the negative takes over. If C2 is greater than C1, then the positives are going to win. Or if both of these are positive, they're never going to be negative here. So, okay, that's a strange looking group of curves. What is it telling you? I can't tell anything, but it's in the book, so I wanted to do it. It took way too long doing that. But they're leading to sometimes a differential equation possesses a solution that is not a member of a family of solutions of the equation. That is a solution that cannot be obtained by specializing any of the parameters in the family of solutions. Such an extra solution is called and this has nothing to do with this one, but now we're, like I said, this whole part here is just giving you definitions. That is called a singular solution. Let's get away from purple, okay? Go back to black, okay? A singular solution. Now, I kind of hate the way they use words here. If you were doing complex variables, a singularity would be a place where, you know, you have a discontinuity in the z-plane. That's not what we're talking about here, okay? It's a singular solution. It's not the same as a singularity. For example, and this was one we did last time, y is equal to 1/16 x to the 4th and y equals 0 are solutions to this differential equation. dy dx is equal to xy to the 1/2. Okay? Now, I don't know if you remember that. When it gets out there, you can go back to last class, and it's example 3 on page 5, the A part. That's the differential equation. We saw that one of these is a solution. They're introducing another one that's a solution. Okay? Now, those are solutions to the differential equation throughout from negative infinity to positive infinity. In section 2.2, which we're getting to, will show that that differential equation possesses a one-parameter family of solutions, and that solution will actually be, this is just one solution, the actual family of solution would be y is equal to 1/4 x squared plus, plus c squared, okay? We're not there yet, but we saw this is a solution. There's a solution, okay? This solution is one particular solution of this, where c is equal to 0. That will give you exactly that. But that's not the only solution. You could have where c is equal to 1. There would be another solution that would work just as well as this one in this equation. You can try it and see for yourself. The thing is, you'll never get this out of that, right? It's not going to happen. You can't come up with a c that's going to give you that. This is a singular solution. This is just one of a family of solutions. One parameter family. That's what they're getting at. That was the reason they did that, was to illustrate what a singular solution is. Okay. So let's do example 7. One we haven't done, so let's go to example 7. Here are two functions. X is equal to C1 cosine 4t and x equals C2 sine 4t. Okay? And C1 and C2 are arbitrary constants or parameters, and they're both solutions to this differential equation. X double prime plus 16x is equal to 0. Just a little bit of an explanation here. Notice when we say x is a function of t now, not x and y is a function of x. X is a function of t. So when we say x double prime, that's second derivative of x with respect to t. Okay? So what have we got to do? You got to take your both first derivative, x prime is equal to this one.
Yeah, I was going to ask you, which one is?
What's that?
X have a problem, first one, second.
Okay, this one. The one I've drawn.
Okay, so the plus 16x would be the second equation.
Okay, that's a differential equation. I probably shouldn't have written it in there, or I should have allowed more room to do these otherwise, but let's just skip down and do the first derivative of that first equation. What would that give you? Okay, C1 is certainly there. 4C1 is certainly there. Minus 4C1 is certainly there. Sine 4T. All right, okay. Now, let's do the same thing to the second equation. X double prime here, X prime here, sorry. Ultimately, we're going to do a double prime, but let's not yet. Okay. Maybe one of these days I'll get fast at this, but I doubt it. Okay. Let's do this one. 4C2 cosine 4t. Got it. So let's do the x double prime from that first one, and what do we get? Negative 16 C1 cosine 4t. And x double prime for this one would be negative 16 C2 sine 4t. Very good. Okay. Now, let's plug either one of those back into the first one. Let's do it here. So the first one would be minus 16 C1 cosine 4t plus 16, plug in x, C1 cosine 4t. Sure enough, that's equal to 0, right? For any value C1. Okay, let's do the same thing for the second one here. X double prime here was minus 16 C2 sine 4t plus 16 times its x C2 sine 4t. And guess what? That's also equal to 0. So both of those are solutions for that differential equation. Okay? Two parameter system. In a second order differential equation, you get two independent parameters. Now, there's another part of it that wants to say, is x equals 0 also a solution? Yeah. Can x equals 0 come from either one of those? Well, sure, when t is equal to 0, well, no, that's a variable. Yeah, if c were 0, that I think would do it for us. What was their point here? I mean, maybe that's not the point. Okay, so this one doesn't have a particular solution necessarily, but here's what we get. Your solution then would be the linear combination of those two. So your final solution would be x is equal to C1 cosine 4t plus C2 sine 4t. Okay? and there's your solution, okay? And if we did derivative of this, it's just doing both of them at the same time, and sure enough, you would get equal to 0. So that is your family of equations. Now, it looks like they're actually graphing this one. No. Yeah. I can't see what the graph is doing here. No, maybe that graph has nothing to do with this one. I thought it did. It's the next one. Okay. How are we doing on time? Is it? Oh, isn't that sad? It's supposed to be at 10:45. Oh, sad, sad, sad. Oh, I can't wait to get out of this section. The main portion of this section is to give you the nomenclature. That's what we're trying to do. But look, we're almost through. Okay, so we'll start next time in example 8. Homework exercises you can do here, any of the odds 1 through 7. If you need to take a picture of my problems here, you can. Either 11 or 13. Either 15 or 17. Do number 19. Either 21 or 23. 25. Either 27 or 30. No, wait. Stop at 20. No, stop at 23. So any of those and the top part here. You can go and take a picture of the whole page, but you can stop at 30. I'd say 23. Because the last ones are
so 1 through 23 on the odds.
Any of the odds that you want to do. I mean, do some of each group.
Right.
But you don't have to do all of each group. But if you're having trouble with them, do as many as it takes till you say, okay, I've got it, move on to the next. Okay. Good. All right.
That's it.
Yeah. I really want to get to real doing the differential, but you really need to know the language. So this first part is to give you the language. I'm sorry it's so slow. All right.
Do you have like syllabus this time?
Yeah, it's on integrity. On Blackboard. Yeah. It's out there on Blackboard.
How do you sign on the Blackboard?
Oh, wait. No, I did put it out. Yeah, it's on Blackboard, I think.
How do you sign on the Blackboard?
Oh,
I don't have all that.
yeah. Is it your...
Do you know your student email?
I think your student email is listed there.
Because whenever you sign in,
Yeah.
Okay. We'll see you Wednesday. No, what's the date? Thursday. We'll see you. I'll see you tomorrow too. Yeah, okay.